Or I'll draw the graph. This doesn't matter. So today we are looking at inverse trigonometric functions. This is a bit analysis, but we need them for solutions of interference effects we are looking today. Then we look at a very cool example. And this has to do with exercise 1 of this sheet. And then crystallography, which is also a very cool topic. And it's like studying the internal properties of a solid. So very small distances and very small effects. So the first bit is maybe the most boring one. And then we are done. And then you can use it for the exercise. And we can look at the more fun things. So what are inverse trigonometric functions? The idea is if we have an equation of this type. So sin x equal a, or similar for cos x and tan x. So what is x? And what is the problem? Sin x, now I'm really focusing on how to draw it. So this is p half, p 3 half. This function makes like this, and this. Then cos x, so cosinus is shifted by, so this is really correct, like this. So this is sinus of x, cosinus of x. Then we can, and then here like this, and here. Great, good. And maybe I should choose another color. And then we also have the tangent, which makes like this. If I'm this, and then this. Something like this. So the problem is that the functions are not injective. You know the concept of injective? So we have if f on x equal a, it exists more than one x2 which satisfy the equation. So if we have sinus of x equal a, we have to look at all of the possible x. And then, of course, maybe in some cases, only some of them are valid solutions, but we cannot just take one random x and say, this is the solution. So why this? Because of, so we have the periodicity condition. This is also for cosinus. And the tangent has a, or tangent, yeah, tangent has a pi periodicity. But this is not all, because with this we are looking at like, this point here, so with a 2p periodicity. But if we look at this point, this is also here. So we have more solutions than the 2 pi periodicity. And this is given by the relation, so sinus of 2 pi n plus 1 minus x is equal to sinus of x cosinus of minus x plus 2 pi n cos x, and yeah, this is all. Yeah, n is an integer number, like in general. So from these, it follows now. We are not showing them because I think you did it sometimes during your analysis or mathematics course, and it's not the purpose of this course. The purpose of this course is that you know all of the solution. And I guess you in the exam, you can bring a 2-sheet summary. I would say you can write them somewhere very small, or it's not the most important thing, but if you have it for an interference effect, like exercise 1, 2 of this sheet, you need this. And if you have the formulas, you can use them and just plug it in. And so these are like, this corresponds to this relation, and these correspond to this relation. And arcsine is arccosinus. You all know what I mean? Great. Good. And then we have the same for cos x equal a. Then x is equal minus arc cos a plus 2pn. And x is equal arc cos a plus 2pn. Again, this corresponds to this relation, this corresponds to this. And then we have tan x equal a, then x equal arc costangent of a plus pn. Any question about this? So the plug-in wherever you have such a relation. Of course, sometimes you maybe have a coefficient or a plus in the parentheses, but this is just the general solution you can use. Now, as a small additional comment, so what is the domain and image of trigonometric function? So if we have the sinus is a function which maps any number, any real number, from -1 to 1. You can see there in the graph. And the cosinus same. And for the tangent function, what you have to be aware is that if the cosinus in that point is 0, then it's not defined. So it's minus or plus infinity, as you can see in this graph. And this is exactly given by this form here, which means between minus p½ and p½ not included. Here the function is defined, and then it's defined here and here, but exactly on the multiples of this, it's not defined. It's minus or plus infinite. And this maps to R. What about our cosinus? This maps from -1 to 1, so it's kind of an inverse function. So it makes sense that this is the domain. If anything is unclear, stop me. But this it cannot map to wall R because it's not an injective function. So this maps per definition from -p½ to p². Our cosinus same domain, because it's always cosinus is between -1 and 1, and this maps from 0 to pi. And arcus tangent, per definition, we choose the domain between pi half, minus pi half and pi half. So these, and then it maps to R. No, sorry, this is exactly the R to minus pi half, yeah. Minus pi half, and then I will draw it, and hopefully it becomes clear. So this is the image of this function. So I take as a kind of an inverse. It's not perfectly the inverse. This is as the domain, and then I choose an interval where it's mapped to. And then I will discuss also why I'm talking about this and why it's important. So here, let's make a little bit nicer, like this, yeah. So for arcosinus, we have it from minus pi half to pi half. And then let me use some colors. And if this is minus 1 and 1, this is how the function looks like. And then, so this is arcsin. And if we have arc cos, arc cosinus, this is arc sinus. And last, we have the tangent function, arcus tangent, which is something like this. So here we can see domain and image, like the intervals where they are defined. Now, this is pure like analysis or mathematics. Why did I show this to you? Because we are looking at interference, and later we will see, but sometimes we have that the probability of something is equal B plus AE alpha, something like this. And from these, you know that, for example, e to the I alpha plus e to the minus A alpha, this is 2 cos sinus of alpha. These are the definitions of the, or definition properties of, and for sinus, you have a minus here. This means that while calculating these, you will become some trigonometric functions. And then why am I talking about the domain? Because you can do some checks. You know that a probability is always between 0 and 1. Okay, so this means that if you have an arccosinus, for example, arcsinus of x plus 10 pi, for example, you know that this is between minus pi half and pi half, plus 10 pi, it's surely greater than 1. Okay, so this means greater than 1. This means something is wrong. And if you have then such a result, you can go back and check your calculation. Is this principle clear? Any doubt? Same is valid, of course, with also arccosinus and arcus tangent. Now is maybe a bit abstract. We will see later in the calculation, and you will also see, especially in the exercise sheet, because there you really have to apply this formula and find out what you have. So yeah, this is. Any question about trigonometric functions? And I would actually clean the blackboard so that you can quickly think about it. And then we start the second part. Sorry. Now we look at an experiment which won a Nobel Prize 4 years ago. So something actually cool. The waves. Okay. So it's absolutely not my field. Probably some expert would kill me if he or she hears what I'm telling you. I just try to make like a simplification to see the connection with the exercise 1, which is kind of a simplified, or like, yeah, it's very related to how they detect gravitational waves. So probably, oh, maybe few knows more about me, more than me about this. So general relativity, and this you probably any people on heart or a lot of people, even if you're not a physicist, you know that this is the theory funded by Einstein mainly. And among many other things, it tells that if there is mass, we have a curvature of space-time. And with space-time, I mean like a vector which includes the coordinate of the time and then spatial coordinates, which in our real world is like x, y, z, three dimensions. And what does this tell, or what does general relativity tells? That from a curvature of space-time, we have gravity. Like, and with gravity is like the gravitational force we have here on Earth, and that's why objects fall down. This is like a generalization. And it also tells that the larger the mass is, the larger the curvature. So this is, yeah, again, simplified version of what general relativity tells. And it tells also something additional, and it tells that if we have an acceleration, we have changes in the curvature. And these changes, they propagate as waves. They have a wave behavior. Curvature changes, And this changement, like, yeah, they really go as waves. And these are called gravitational waves. And these gravitational waves is something that Einstein, or well, actually not only him, he has a lot of credit, but also other people, work postulate them theoretically. So it was a purely formula and calculations. Now the idea is we want to confirm experimentally, like see if these kind of waves really exist, because the theory is nice, but not very useful if we have no confirmation. So, for example, a collision of stars or even planets or bodies causes an acceleration, and there we have gravitational waves. So, gravitational waves. There are also other effects, but it's just if you imagine large masses which are involved in some kind of effects, and then gravitational waves are kind of produced or So then what does a gravitational wave do? Why are we asking ourselves this question? Is because we want to detect it. So to detect it, we should kind of think about an experiment where what the gravitational wave does affect this experiment setup. And the thing is that it stretches the space in one along one dimension, or like one direction, and it extends the space along the other. And this, for me, is a bit not very easy to understand, but the fact is that if I have here this table and a gravitational wave passes through it, this table will be kind of stretched a little bit in this direction. And so, no, stretched is actually here, so it will become shorter and then extended on the other. So this is, of course, simplified, but I think it's exactly what it suffices to know this to understand the experiment. We will look at it in 1 minute. And if there is any question, please tell me.
These two-dimensional changes, are they like inverse of each other, or are they both in the same direction? So if one direction goes bigger, all go bigger, or do the others counter it?
So if one direction goes bigger, then the one perpendicular to it goes stretches. Yeah, exactly. Yeah. So this is like, yeah, exactly. So perpendicular direction, and then one is stretching, the other is extending. But yeah, and I think, yeah, it's not by the same amount of length, but this won't matter for the exercise. And I think it's also quite a lot of formulas and similarity. So now the question is how to measure these changes in space. And for this, we consider an experiment, and now we are probably doing it more general. We are not exactly speaking about gravitational waves the whole time, but then we come back at the end. And maybe you can also think about it while we are doing the experiment. What's the point? So the experiment is a beam splitter, which you know from some lectures ago. And we have an incoming ray, like a beam, incoming beam. And then this beam splits. Half of it goes up. And we position a mirror here. Then here there is such a mechanism that the wave is completely reflected here at the mirror, just with a little bit of space in between so that these two don't interfere, but it's not a problem. Just think about it, this comes back. And then the effect is here, it just transmitted. The whole waves, because of some properties of the mirror, here we assume full transmission. Now, let's write it. Draw it in yellow. Now we have the other waves, because of course, half of it, like the other waves will be transmitted. And we have again a mirror where we have the same mechanism. Here I can draw arrows, so maybe it becomes clearer. So here I go in this direction, the mirror reflects my wave, and I go back here. And then here we have full reflection. Because of properties of the mirror, we are on the other side. So here we have full. And here these two waves therefore recombine. And then we have a detector. Oh, yeah, actually it's a bit like this detector. Then I define this wave as this length, so between here and the beam splitter, as LR, and this LT. This is just notation, and the distance between the beam splitter and the detector as D. Then we work in the approximation or the Hamiltonian. This you saw in the lecture last Tuesday. Yeah. And according to this, so that I'm not deriving it, you can look at the lecture, but from this, it follows that the free propagation of a beam over a distance delta x gives a phase to the state e to the a k x delta x. And this for the exercise you can assume. Okay, you can just use it. Is it clear or anything unclear in the experimental setup? So this is now, we have the experimental setup, we have our wave or state, and then now we finally do some calculation. So we have initial state this, and we work in the basis so this is what we saw in exercise sheet 2, where we worked with a beam splitter and Mach-Zehnder interferometer And the beam splitter makes that T is mapped to, and the way around, T plus R, so transmitted plus reflected kind of states, and this is transmitted minus reflected. So these you calculated in exercise sheet 2, you can use it. You don't have to rewrite it here. So now we have this initial state, which is here. In our experimental setup, and we want to see what happens. What do we have to take into account? This, the phase, and of course also what happens otherwise. So if I have my state tau after the beam splitter, what is the state? No? Yes? Exactly. We just input this here. Plus up. Then, if you look here, so if you consider this mirror, what do we have to include? The state here. We have to include this phase. Okay, our wave propagates from here to here. So this is the reflected wave here, and it will pick up a phase corresponding to delta x equal LR. This state will pick a phase corresponding to delta x equal LT. Okay, so at the mirrors, here I can write beam splitter, mirrors, we will have 1 over square root of 2 of e to the I k delta LT. Sorry, this LT, this is delta x, plus e to the a k L R R. Yes, yeah, like I wrote here or LT to an L subscript R, but it's just notation. Just that this symbol is exactly this symbol here. It's like the length, which is my delta x. Now, if I come back to the beam splitter, what do I have to do? Yeah, just before the beam splitter.
So you've got the same distance again.
Exactly, yeah. So I will have here, so before the for BS beam splitter second time, we will have 1 over square root of 2 of e to the 2I k L t plus e to the 2I k L R R. Now we are here. What do we have at the detector? We again freely propagate, yeah?
Don't because we just reflect the beams as a relationship.
Exactly, yeah. So, but we still have to add something. Yeah, so this is the phase which picks it from here to here. Okay, because it travels again a distance of d, this small d. And these, so at the detector, we will have e to the I k d. So this is something which both rays or beams pick up. So I will have it like this over square root of 2 I k L t plus e to the 2 I k L R R. So this is a global phase. And as you probably remember, global phases are not detected experimentally. So these we can neglect in a state. Now, if you think about, you probably remember this experiment you saw in the second week. And this is a perfect, so here is L divided by 2, L divided by 2. And you had a beam, incoming beam, this is a beam splitter, this is a beam splitter, and these are two mirrors. We didn't consider this phase, okay? Because at the moment we couldn't think about, we didn't know about Hamiltonians and these kind of things. Is that a problem? Yes?
I mean, in our case, now actually it will be a problem if we don't consider the relative phase between the points.
Exactly.
Because in the end, there's going to be interference when the gravitational wave or something else hits the thing, and that's what we can use to detect.
Yes, yeah. So the fact is here, in this case, we would have here a L and here a L, which is exactly the same. So we can bring it in front because the length of this path and this path is exactly equal.
But if it's not the same, then we can...
Exactly. But in the Mach-Zehnder interferometer, it was the same. So we actually made a mistake or neglected this, but it doesn't affect any of the results we calculated in the exercise sheet 2. Is it clear? Something? And yeah, exercise 1 actually includes a different path length between the two. And this is exactly where you have to then include the phase, the phase, and you will see how it changes. Great. Then where am I? Here. And yeah, we can write, so at the detector, I write the incoming, so the state of the incoming ray. This will be AKD, right? Square root of 2, and then I just, for simplicity, take this out, L plus e to the IK LR minus LT, and then I have a 2 here, yeah, and then R. And this we can call it delta L. So the difference between the path lengths of the two ways. Why do I introduce, or actually I can call it, let's write it, it's actually even nicer, 2L minus 2R, this delta L. Why this? Because yeah, this is, as just said, global phase. And we can forget about it, okay, kind of, for our measurements. So this is done. Then the question is, yeah, how to detect a difference, yeah, a delta L. So if I calculate the probability of Oh, this is a T and not an R. Yeah. If I calculate the probability of measuring T, this is 1.5 actually, because here I have 1 over square root of 2. And this is also 1 over square root of 2. You see, because this is like the absolute value of this is 1. So the idea is shows projective measurement in another basis. For example, I could use in psi1 equal plus r and plus psi2 minus r. So if I calculate the projective measurement of it, I will take, so P of psi1 is equal to psi1 psi incoming. And the probability of measuring the second state will be the same with the second state here. And this will give me here and this is square. This gives me, so the first gives me 1 plus e to the I k delta L square divided by 4. And this gives me 1 minus e to the I k delta L square divided by 4. This, yeah, is simple calculation and not doing the steps. You can check it at home if you want. Here, again, I can do a check a bit in the direction we saw earlier. I can see that this is 1, and this is between -1 and like also complex, but the maximal value it can take is 1. So here I have 1 plus 1 square, the over 2 is, yeah, square, which is 4 divided by 4. So my probability is maximum 1. So it makes sense. It doesn't tell that it's absolutely correct, but at least it doesn't tell that it's wrong. Same here, the minimal value is -1. I have 4 divided by 4, it's 1. And this is also always positive, which is also another check. So how can you detect if there is a difference in the length of the path? If the probability of one is different than the other, then it means delta L is unequal 0. If we have delta L equals 0, the two probabilities are exactly the same. No, actually, wait. What I'm telling you, if L is equals 0, no, then we have 1 and 2. Yeah. If phi 1 is equal 1 and phi 2, because if we have delta L equals 0, this gives me 1. So this measurement is exactly 0. So all of the measurement, we will measure only a superposition with state phi 1. Is that clear or something missing? The idea is really putting in the values and see what we get. So yeah, now we can take a break of 10 minutes, and afterwards we see, now we will see how actually what this probability means, or how can we relate an experiment, because this is only theory calculation, to a delta L. And yeah, we reconvene in 10 minutes. And if you have anything you want to discuss, I'm here.
question from ETH Solution.
Yeah. Oh, the last week.
No, not last week. The week before.
Before we go. Okay. Yeah.
And I was wondering about an integration step. Where we integrated a phase-shifted cosine function.
Yeah. This maybe or
yes.
Yeah.
You pressed it. You changed it. Right?
No. Wait. Week 5. It's Nuriya's or was me? No, this was me. Week 5. Yeah.
Okay.
No, wait.
So you have to
no.
always do.
No, this is the Nuriya. Okay, yeah.
Yeah.
So maybe she corrected it. Because, yeah.
Mm-hmm. So you have to always do it via the exponent. There is.
Yeah.
But the problem is that you are integrating over real numbers, but you have complex.
Yes. But this is like splitting it. So if you integrate A plus EB from minus L to L, it's
You can split just in the
complex and the real part. Exactly. Yeah. Yeah, exactly. Yeah. Is that okay? Great. Yeah, this was it you asking? I think there was a cosinus integral which was not clear, and then she added some explanations. I don't know. It's that one, exercise sheet 5, or yeah. Okay, then it's this week she added some explanations. Yeah. Great. Good. So we can go on. And we'll come to the most exciting part, in my opinion. So now we have this setup. We have our probability to detect our beams. And then the question is how to determine delta L, because this is usually what we don't know. And 2 is how to detect gravitational waves. So first, let's go to 1. So we have what is theory and what is experiment. So in theory, according to theoretical calculation, because it's not, we have psi1 and psi2, which actually they are related, or so one is enough because p psi1 plus p psi2 must give 1, so one of them is enough. And in the experiment, we have tries, or tries. So we know that one try. So, try detected in psi1 or psi2. Now the idea is very similar to the to a coin. We know that a coin has a head or a cross. So we know that actually in half of the time we expect a cross and half of the time we expect a head. But if you launch it once, this doesn't really give indications. It's 100% one of them. If you launch it 10 times, it can happen that you have 10 times heads. If you launch it 1 million of times, this is basically impossible. Or like the probability is so low that you should spend your whole life and the whole life of the universe to make it happen, that you have 1 million times only heads. So we can say that for an n sufficiently large, large, the probability of head is approximately 1/2. Is that clear? Here we do exactly the same. We say that for n sufficiently large, and so the number of times that we will detect our state in psi1 divided by the total number, it's approximately p of psi1. And the same here, n of psi2 divided by n is approximately p of psi2. And this, I would call it p of psi2 experimental. And this is also like our experimentally measured probability, psi1. So this is exactly my definition. I can also even write it like this. This is something we expect to happen. Is that concept clear? So this is really the basis of our calculation. So then we have, so to determine delta L, we have set ni1 divided by n equal 1/4 of 1 plus a to the I k delta L squared. And solve for delta L. Here we will have some cosinus or sinus of delta L, of something multiplied by delta L. And that's where we have to go back to the first thing we saw this morning, inverse trigonometric function. What does it mean? So here, attention, so multiple solutions. So of course, in the experiment, we have one delta L, so the difference between the two is well defined. But with our interference experiment, we can determine it up to some periodicity conditions or non-injective conditions. So it's not that we have the full answer. Sometimes then maybe we know it approximately and then we can guess it, or we just don't care and it's enough to know that there isn't a delta L, or that is this experiment to theory connection clear? So now we go back to the even more exciting part of this exercise class, which is question 2. So how to detect gravitational waves? And to tell you, so the principle is, what is the problem of these gravitational waves? So why do we design this complicated experiment and everything? So they are very small. If two huge stars collide at some light years apart from the Earth, then we have, like, for L equal 4 kilometers, so imagine something long 4 kilometers, the range of the size of the gravitational expected is of grav waves induce a change of length of the order of 10 to the minus 18 meters. Okay, so this is 4 times 10 to the third meter. So 21 orders of magnitude bigger. This is bigger, yeah, like this is 21, which is with non-experiment, like no measurement of the length can detect it. This is absolutely impossible. So what's the idea here? If we proceed in that way, we will have 1 plus e to the a k delta L. Okay, or yeah, let's gravitational waves. So yeah, let's go back to the experiment. In the experiment, there are some detectors, I think at least 2 in the US. And we have that LT is equal LR and it's 4 kilometers. Yeah, so these are exact, which if you think about it, already doing this kind of thing that they are exactly long, exactly the same long, it's already a challenge. And then the idea is really that they measure stuff and they wait for a gravitational wave to happen. And when a gravitational wave happens, then we know that if the wave, for example, goes like this, let's write it. We know that LT will be an LT plus some delta L, like this, and LR stretches. We'll write it like with a point like this. So we have a delta L, which is of orders of 10 to the minus 18. If we input it in what we found before, we had like P of psi1 is equal 1/4 of 1 plus e to the I k delta L. And this is of order of 10 to the minus 18. Now, what is k? Because this is what it's multiplied by. So k is our wave number. And it relates to the wavelength as k is equal to 2p divided by lambda when this is the wavelength. And the wavelength is if we have the probability amplitude of our wave, so this is lambda. Now, the experiment for detecting gravitational waves, it doesn't have really a transmitted beam, a beam in a transmitted state, but incoming beam is white light. So incoming beam, so experiment, the incoming beam is light. And light has a wavelength -7 meters. So in the order of nanometers. If we rewrite this, so this a to the a k delta L will become a e to pi I delta L divided by lambda. And this is inputting this formula here. And now we have here are 10 to the minus 18, and here 10 to the minus 7. Then, of course, sometimes they use just, but here is to give you an idea that, of course, they are not very, like, they are still far apart. But we went to 10 to the 3 and 10 to the minus 18 to 10 to the minus 7 and 10 to the minus 18. So these two variables are way more comparable. And if we have the larger the delta L is, then of course the function is periodic, but this is still very small. And if you think about a sinus of x, here it changes a little, like in a very close to 0, it doesn't change that much straight away. It's approximately 0, but at least you can detect it way better. And another problem is here we looked at the experimental detection. The idea was to send many beams, a large number, and calculate the probabilities, like many photons. You can send many photons in the state T and see how many you detect in one and the other. What are the two probabilities, and then calculate L. A gravitational wave is a millisecond or way less. We cannot send many photons. So their idea is that they send light, and for this I'll bring here back. And here we can really think about it in wavelengths, like this. And this wave will be reflected and then comes back. And then is here. I should have done it, yeah, okay, in red. But now let's keep it blue. And then I'll take another colors. Now let's take in yellow. So here we have this. And because of this length difference, these waves are not in phase. So here we will have an interference effect. So what do they do? Is it's really like that. They have a couple of interferometers, exactly like this, 4 kilometers long, somewhere around the world. Very complicated setup, very expensive. And then they measure the light incoming here, the whole time, like 24 hours per day. And if they see just a normal interference effect, then they see, okay, it's everything as normal. The waves are in phase. We don't have a delta L. If suddenly in some milliseconds, they observe another interference effect, this means a gravitational wave passed through the interferometer. Is that clear? So the chance of getting it, it's not very high. And that's why these experiments, the first time they did it, they won a Nobel Prize. Just to tell the importance of this. And of course, you have to be lucky, which is, the gravitational wave has to pass through where your experiment is. And of course, then they don't look at the interference pattern at every millisecond, but they have some system which, if something changes, it detects it and will give you the image in that point of time. And I also think that the gravitational waves has to go quite in the direction of the, like if it goes in this direction, then you don't really see a difference. The key effect is really that it's parallel to one of the two arms. And these experiments actually, of course, then they are optimizing it and everything, but it was, I think, also conceived, Einstein designed like the thought experiment. Then the technique came way later, 2016 or 17, the Nobel Prize is 16. Great. Then I think that we are done with this, and I'm missing place. Yeah, and then great. So yeah, these waves you can really look. So this is light, but you can really look at it as the amplitude of the wave function. If you remember, we wrote like these are psi of x. And then, for example, for an envelope, we had it like this. But for normal, like, yeah, just if you have e to the ikx, if this is my wave function, like this, yeah, then this gives me like this. This is also this particle wave dualities. We have a particle which behaves as a wave, and this is this amplitude which has also wavelength, a wave number, and so on. Great. Any question about this experiment? We have still a little bit of time, so if you want to discuss, just tell me. Now we move to another part, which is crystallography. And it's actually something completely different. If you look at the research group doing this and research group doing this, they are like, yeah, like black and white. But the funny things is that also in this case, we use interference effects. So the basis is the same, the physics completely different, sizes of experiment completely different, and everything. So what is the idea? Is the study of microscopic properties of solids. And we know that the atoms in solids are usually arranged in such a place. And there are also, not all of them have a cubic structure, but there is distance between the atoms. And we have a periodic structure if the solid is a pure material. And of course, there are also impurities, like mix of many materials, but this is what we expect. And actually, we expect it also because of experiments. We know, yeah, we will just look at it in a couple of minutes. What is the distance here? It's larger than gravitational waves, fortunately, but we have 10 to the minus, which is view. So already this sign symbol, it means 10 to the 1 angstrom means 10 to the minus 10 meters. And yeah, as we know, light has 10 to the minus 7. So if we conceive an experiment of this type, then you will see it's not exactly the same experiment, but you will see we have a to the 2 pi e to the 2 pi a 10 to the minus 10 divided by 10 to the minus 7, which makes it quite interesting. And what's the problem? So you probably all know that we have microscopes to detect, like to observe a small structure, but the microscope is can detect, is like detects objects, or can differentiate objects which are maximum 10 to the minus, minimum 10 to the minus 7 apart. If they are closer, the microscope cannot differentiate between the two. you can think about, yeah, like if you look at something very small, you don't see all of the electrons composing an atom because our eye is not capable to do it. So what's the idea? We have to, if we want to look at the different atoms of this structure, we have to use different methods. And one of it uses interference effects. And in exercise 2, you have a simplified version of such an experiment. So order solutions. So we have a crystal, and we know that a crystal is composed by similar structure. And we have a source, a beam, which goes to the crystal. And then as some atoms are here, so a part of the beam will scatter out. It will be kind of reflected. So if we have a beam going to an atom, this will reflect. But if we have a beam just passing through, not hitting any atom, this will transmit. Therefore, we expect a transmitted beam and a reflected. And this we don't care about. So like this, we just forget, or I mean, it's there, but it doesn't give us any indication. We will see it now. Why? Yes? This is absolutely wrong. This is transmitted, and thank you. Transmitted, and this, let's call it scattered. Thank you very much. And here we have a detector. Now, this solid has a microscopic structure. So in the exercise, this beam is composed by many, so the beam, when I draw it like this, I mean that if this is the source, there are many parallel beams going out of it, which are very close to each other, so infinitely many. But in the exercise, we treat them discretized. So our state is kind of a sum of some set I. Yes? Yeah, this is again particle wave dualities. Yes, we can take this as a source of light, and okay, I know what to tell you. A source of light which is composed, it doesn't have really a finite number of photons composed by it. Yeah, exactly. But you can also take it as finite. The fact is that if you have here an atom, that what we have to assume is that there is a ray hitting it. This is why I'm telling you infinite many, because they are infinite close. But you can also tell, okay, I have a finite number of beams, but this condition is satisfied.
For example, like with the side but also outside the
Okay, now for us in this exercise, an atom is a point particle. Of course, you're right. It depends on the wavelength of this light, if it's capable of even scattering like electrons or not. If it's some dimension, if you imagine this is the atom and this like this, and then we have a, I don't know, wavelength like this, then anywhere it hits, it reflects. Of course, we have to do many assumptions because reality is very complicated. And that's also why I'm discussing it here, because I think if you just read the exercise, it's a bit tricky, but we didn't want to write just 5 pages of explanations. So yeah, the important thing is to think that this is how they are emitted, and if this is my surface, this is an angle theta. So let's take it as the upper beam because it's what the exercise does. So I tell that here we are at x equals 0. So you can imagine that this is so far away that each of them are emitted, or let's take like this, yeah. Here, x equals 0. And then this means, and here is x equals d1. So this, let's assume that exactly at d1, this ray, the upper ray, hits an atom here. So this distance here is d1 divided by cos of theta. And this is trigonometric. And we call it, for simplicity, d. Now, let's take the beam. If here we have another atom, we will have a beam which is this. Let's tell that this is psi 1. And this, I call it psi j. It's just one of the beams. So here, psi 1 will go from this state here to e to the akd psi 1. Because it propagates over a distance d, it picks up this phase. Is that clear? Now for psi j, I have to do the same. But this distance, so the distance between here and here and here, let's call it d2. This is not d. If we draw here a 90-degree angle, this is exactly d. From here to here we have d. But here we have an additional delta d. And this delta d, you can determine because of the geometry of the problem. So think about it. This is an angle theta. This is also an angle theta. Or, yeah, sorry, it's quite small, but here this gives you theta. So see what is the length difference here. Then these rays, if they hit an atom, they will scatter. And now I have this. I will do like this and this till my 90 degrees angle to the incoming beams. So here we have a. So here, if I have that this is at d, I will have that this length is d minus d1 divided by cos theta. And this, you can assume, these are some law of physics, that if a beam is scattered at angle theta, it will, so if the incoming is at angle theta, it also scatters at angle theta. So this is the length of this. So my state will pick up this phase, d times e to the a k d minus d1 divided by cos theta psi 1. And then what happens for beam 2, 3, and so on? So beam j, or like the beam eating this atom, the beam eating this atom, the beam eating this atom, and so on. So the resulting beam, the incoming in the detector, will be a sum of some beams n, the one eating these atoms. And in the exercise, you should only considering the one eating the atom exactly at D1. Actually, if you look at the interference conditions here, the rest follows along, and otherwise it would be too complicated. So just consider the beams reflected here. And this will be some phase of the sum of the beams which are scattered. And with this, the exercise is to see, okay, when will we have a maximum amplitude? When we have constructing interference, destructive. And then the most important thing, which is exactly the field of crystallography, is how do I determine the length of this? If I have a beam, which is constructed exactly like this, I know the distance between my beam and the crystal and the detector. I know at which angle I will input it, or I can control the angle, but I don't know delta L, which is, yeah, here we can call it delta L, which is then exactly here. If the atomic spacing is the space between the atoms, it's this delta L. So you should try to figure out how this propagation, the difference of propagation is related to this delta L. And once you have the final function, how can you infer delta L? Which is a bit, if you think about that, the idea is like we have the experimental results of the probabilities because we send many photons, for example, or we have a different pattern, and then we go back to delta L. Here is exactly the same. We have an incoming beam, which we can detect, and we want to go back to the atomic space. Of course, here, then it's not anymore that two paths have different lengths, just these beams, then they have a superposition. And also here, as a last comment, we can think about it as waves, because they have a wave character. So if at the beginning, these beams are in phase, so these will be also like this, where one has a maximum, the other has a maximum. But as here, this beam travels a little bit more, then it will have maximums. Not if here there is a maximum, here we don't have a maximum. And same for other waves. And the resulting waves is the sum over this, which then gives our the amplitude of the wave, of the beam, of the resulting beam. Does it make sense? Great, then I'm done for today. If you want, you can start solving the exercise. I will stay here just for 10 minutes or having a longer break. And yeah, the lecture will start at past 12, yeah, sorry, past 12, yeah, no, past quarter past 12, yeah, exactly, yeah. And we'll see each other in 2 weeks, yeah. Oh, no, sorry, here I can leave it.